really concentrated towards C. You have as many people getting D's and not even able to make it through as you're getting B's, and 2 people ever have failed the math exam, and I tell you, it was just barely, and have gotten an A. Okay, that's 2 people out of 304. That's 5% of all students that did not pass the exam outright, and that's 0.7% of all students. So if you think you're the exception, that's great. Okay, I wish you well. I hope you the best. Okay, but I am trying to tell you right now that if you're looking to get straight A's and be a competitive health profession school applicant, then you should maybe slow down and take a pause here. These marginal fail students, I'm going to recommend ALEKS, which is the math drill system. Do it early, do it to get yourself up to speed. While you're at it, I'll throw in, eat healthy and exercise regularly and other things that are good for you, okay? You really want to make sure to do it. For people who are in this very last category, I need you to see me and talk to me, okay? So we really need to assess what is going on. Yeah? It's on WebAssign. Everything in my class gets posted on WebAssign. Question?
Just to note, we divide our score that they give us by 45.
If you took it at the testing center by 45 to get your percentage, because that's the total. If you took it the makeup exam, it's out of 50. So if you took it in lab, it's divided by 50. The testing center scores, I believe, are reported to you individually. If you took the math exam makeup, those are available. Probably the first access you had to it is on WebAssign. Okay? What's that?
Where in WebAssign? It's not under grades.
Under where everything is on the home screen. Okay. Okay, so that's my warning to you. I hope that you prove me wrong, but physics is basically applied math, so you shouldn't try to take advanced math if you have trouble with beginning math. If you have a chance to take a look and maybe, especially for those of you that did not come in with the summer class, most of you took either pre-calc or higher as your math class over the summer. If you skipped all that, then you're already at a potential deficit. So you might look into taking that first. Okay, so that's enough preaching about the math exam. I hope you all prove me wrong, but just these are the statistics. Are there any questions on that before I move forward? Okay, so again, check your score right away. If you do appear in the fail category, I do need to see me right away. I'm not going to, come chase after you. At some point, I'm just going to make you come to me. I'll shut down your WebAssign or something if you don't get in contact with me, if you're in that fail category, okay? So, kinematics. Let's review what we need from last time and then build on it. We talked about the relationship between velocity and acceleration. If they're the same direction, then the acceleration reinforces what the velocity has going on already. You'll speed up. If they're in opposite directions, either one being plus or the other one being minus, then the acceleration is going to instead counter what the velocity is doing. They're in opposite directions, going to slow down. Other things that we will commonly assume that we have constant acceleration, especially in homework 2 and beyond. There are several very complicated motions in homework 1 which are not constant acceleration by any means, but I also, of course, limit the complexity of things I ask you about them. Constant acceleration is smooth velocity changes. So you're changing your velocity certainly, but the instructions to the velocity on how to change, which is what the acceleration is, those instructions are constant, so the velocity changes smoothly. Now there's one possibility that I want to bring up. There's a bit of an asymmetry between these 2 different options. If they're in the same direction, you'll speed up, and speeding up is something you can do indefinitely. So if we ignore like relativistic speeds or something like that, the point is that there's no upper limit on how fast you can go. However, slowing down is something that you can only do so much until you've stopped. Okay? So what I want to do is an example where I'm going to apply an acceleration opposite your velocity for a while, and we'll see what happens. Let's suppose we have an object which has an initial velocity of plus 2 meters per second. I don't want it to be too big because I want to have it be readily close to stopping. And I'm going to apply an acceleration which is minus 1 meter per second squared. So these are my givens. I'm going to assume this is constant, and of course implied in what I've just drawn is that I've picked plus to be to the right. So let me make a little chart. At what time is what velocity? Time will be in seconds, velocity will be in meters per second. And at t equals 0, which is when I start counting, my velocity is plus 2. So that's my initial stage. Let's see what happens when I apply this acceleration. The acceleration is written in compact form here, but remember what that actually means. That acceleration says to add negative 1 meter per second to the velocity for every second. So after 1 second passes, what will be my velocity now? Plus 1, right? So I have to add negative 1 meter per second every second. After 2 seconds, what's my velocity? 0, because I have to, again, do the same thing. I have to add negative 1 meter per second every second. That's what the acceleration is saying. That's the instructions to the velocity on how to change. And we're stopped. So this is clearly a slowing down. We're slowing down, and in fact, we've slowed down and stopped. But let's take the acceleration instructions very literally and keep on following them. Let's say more time passes, 3 seconds. If I follow the instructions given to me by the acceleration to the letter, then my velocity should now be what? Minus 1. And if I do it for another second, what is it now? Minus 2. So now, the velocity has become negative, which means that the actual direction of travel is to the left. And, of course, you're speeding up. Because you're going from rest, which is the slowest you can go. Now you're going faster and faster, but just in the negative direction. Right? Remember, the negative is just an indicator to the left. You're going 0, 1 meter per second, 2 meters per second. It just happens to be in the negative direction. We can actually draw this. It looks like this. So this would be at v, this would v equals 0 meters per second. That's at, actually this should be like this. It should be closer. If I draw my 1 second increments, of course, I'm slowing down, so I'll travel further during the first second, and then slowing down, I'll travel less in the second second. So this is v equals 0 at t equals 2 seconds. And let me actually draw the acceleration in a different color, so that way we can differentiate. The acceleration, acceleration, acceleration. So even though the velocity has shrunk down to nothing, the instructions persist. The instructions persist on what to do. Well, you can see that the velocity and acceleration are opposite during this. You slow down. But here, even though we're stopped, the acceleration is still there. So what happens now is that the velocity speeds up but goes the other way. It all happens under the same acceleration. So notice the acceleration is always there. I've tried to draw the red arrow, always the same size, always the same direction. The acceleration is constant. It's the velocity that's changing under the instructions. Think of it like this. When you're slowing down, the velocity and the acceleration are opposite. But if you nag the velocity against against the direction that it's going long enough, you'll nag it and get it to join you. Okay? So when you're slowing down, the velocity is positive, the acceleration is negative in this case, but later, the velocity and the acceleration are in the same direction. Because the acceleration is still negative, and to join the velocity, it asks the velocity now to be negative too. So now they're reinforcing. So what would be an example where you could do this, where you would have an object slow down, stop, turn around, and speed up? One example is, if you can do this in your car, what you do is when you're driving forward, I don't recommend doing this too fast, you drive forward and then put your car in reverse and hit the gas. Okay? If you do that on the highway, you'll just ruin your car. But you can do this in the parking lot at slow speeds, and you can see it work. So you're going forward, your velocity vector is forward, throw your car in reverse and press on the gas. That points your acceleration vector behind you. So what happens is at first, it takes away from the forward velocity, then it stops. But then, of course, you're in the situation that you normally should be using the reverse gear. You're stopped, and your acceleration points behind you, so you speed up going the other way. Okay? The idea is if you have pre-existing forward velocity, the acceleration has to work it off first. So you have to slow down, stop, before you can turn around and speed up the other way. Okay? Now that might seem like a contrived example, and it might ruin your car, but let me show you another example. This we'll get to later today. You throw something up in the air. It slows down, stops, turns around, speeds up. That's because gravity works this way. Gravity applies a constant downward acceleration. So if you throw something into the air, the velocity at first is up while the acceleration is down. So then that velocity gets chipped away. It gets chipped away to nothing. And for a moment at the top of the flight, you're stopped. And then you speed up going downward because the velocity joins the direction of the acceleration. So as seemingly complicated of a motion as slowing down, stopping, turning around, and speeding up can happen under constant acceleration. In fact, that's the most complicated thing that can happen under constant acceleration. Are there any questions on that? Yeah?
So when you go on top, your acceleration is, when you go up, what's happening? It just increases?
So this is after it's left my hand, right? The velocity is upward, which means it's going upward, but it's slowing down because the acceleration is acting opposite.
Because of the gravity.
Gravity applies that acceleration. Yes. Question? Well, there's no axis in here. You want to call this positive? Then yes, this is negative. But if you want to call this positive, then this is positive. There's no universal positive axis in the universe. Yeah, you can call this positive, then anything that points this way is positive and this way points negative. There's no plus and minus until you've defined an axis. And that's just the scaffolding that you're putting onto the situation. There's no universal choice. Any other questions? Yeah?
I'm trying to picture negative velocity. So if it's a negative velocity, does that mean it's going, can you picture description?
That means it's going opposite the way we've defined as positive. That's all. So if we say that way is positive, then if you walk this way, that's negative. That's all. So the only thing that the sign in the front means is what direction it's going. This right here, this thing is going 2 meters per second, and it's in the left or negative direction as we defined it. So basically, if it shouldn't bother you if I say that this way was plus, that means the acceleration will be plus the whole time. The velocity at first is negative, then it turns around and becomes positive. This is all just, convention that you choose to put on it. There's nothing wrong with this. And that's really important to understand because we're going to pick some really bizarre axes. We're going to pick that the positive axis sometimes is like this, sometimes is like this, sometimes is like this. And so it's important for you to understand that there's no plus or minus until you've defined an axis, then plus is this way and minus is this way. Okay? So any other questions on that? Okay, so let's just make a catalog of possible motions under constant acceleration. So that's the kind of motion we'll look at. That's the most complicated motion we'll look at. Let's just make a list of all the things that could happen under constant acceleration. And I guess I should say we're of course strictly speaking about one-dimensional motion at this point, but just in case you're looking at your notes later, this is only for one dimension. We'll start with the most boring, where the velocity is 0 and the acceleration is 0 too. What's going to happen? Stays at rest. It's at rest to begin with, and there's no acceleration to change that, so it stays at rest. All right? What if the velocity and acceleration are in the same direction? You're going to speed up. Oh, I forgot. Sorry, that's 3. Let's do them in order of complication. So what happens if the velocity is not 0, but the acceleration is 0? What are you going to do then? You're going to have a constant velocity, right? So you have some velocity, and there's no acceleration to tell it to be different. So then you just stay at a constant velocity. Make sure you understand the difference between constant velocity, where your velocity isn't changing at all, and constant acceleration, where your velocity is changing but smoothly under a set of instructions which is remaining constant. So that's 2, 3, and 4. When the velocity and the acceleration are in opposite directions, what's going to happen is that you can slow down. That's certainly what you'll do at first. But depending on how long you let that go, you may find that you slow down, but then stop, you turn around, and speed up, which is what we just talked about. Of course, for the turning around and speeding up, the velocity and the acceleration are back in the same direction. Okay? It's just that you can start off at the beginning with the velocity opposite the acceleration, but if you apply that acceleration and you nag the velocity long enough, you can get the velocity to switch teams and point the same way. Question?
No, so just for your example, so when t is at 2 seconds, and your velocity at 0, that's the point where everything switched directions, your velocity switched to the acceleration.
That's exactly right. So the velocity, if it's going to be positive, a positive number, which is to the right, and it's going to switch to a negative number, which is to the left, you can't switch from a positive to a negative without going through 0. So you have to momentarily stop to be able to turn around. I should mention that if we're talking about conventional brakes, like the kind you have in your car, it's actually a little bit more tricky. That's not constant acceleration, no matter how you might apply your foot. Because what happens is that the velocity and the acceleration are opposite until the velocity goes to 0. And then what happens to your acceleration? It goes to 0 as well, right? Because brakes stop braking when there's nothing to brake, right? So then your car can just sit there. So your car will only apply the brakes when you're moving. As soon as you stop, the acceleration turns off as well. So brakes actually apply one value of acceleration when you're moving and a 0 value when you're stopped. Okay? So brakes are more complicated, in fact. You may have thought that this was complicated, but this acceleration acts opposite to you so long that it'll stop you and turn you around, whereas brakes have the courtesy to turn off when you stop. So when the velocity goes to 0, the acceleration goes to 0 too. Are there any questions on that? Okay, so that's a little bit about the more complex, or the most complex kinematics you can have with constant acceleration in one dimension. I also do want to say a few brief words about continuity. So, first, I'll explain what I mean by continuity. That means if you want to change from one value to another, you must do so continuously, which is going through all the values in between. That's what we say when something is continuous. This idea that if you want to go from 3 to 5, you have to go through all the values continuously from 3 up to 5. So for instance, position for us must be continuous. This one's the most obvious. If you want to get from a location of 3 meters to a location of 5 meters, we don't have a teleporter. So you're going to have to pass through all the values in between, right? You can't go from one place on the number line to another place without going through the values in between. We don't have a teleporter just to get you straight there, okay? So that one's obvious. What about velocity? Velocity, same thing, must be continuous. So if you want to go from 50 miles an hour to a stop, you have to go through all the other speeds in between, right? You'll see the needle on your speedometer in your car go like this, right? You won't see it go this and then suddenly appear here, right? Now that's even if you hit a brick wall, it'll do that very quickly, but you will have spent some microsecond at all the velocities in between, right? And if you're not hitting a brick wall, hopefully, then when you brake, right, when you try to go from 50 miles an hour to a stop, you know you're going to have to go through the values in between, okay? Acceleration. So let's talk about that. Now, acceleration is the instructions to the velocity on how to change. So for instance, you're changing your acceleration when you're driving your car and you take your foot from the gas and put it on the brake, right? When you have your foot on the gas, your acceleration is pointed forward. When you have, well, that's assuming you're not in reverse. When you have your foot on the gas, your acceleration is pointed forward. When you put your foot on the brake, it's pointed backwards. So you're changing it from this to this. Now, that again does take time, but we're going to neglect that time. We're going to say that you can very quickly, instantaneously switch your foot from the gas to the brake. Okay? You can switch the instructions to the acceleration. So for us, it's going to be okay to switch from one value to another in an instant. Okay? An example, by the way, would be brakes, right? Brakes, you switch from one value of acceleration while you're still moving, and then as soon as you stop moving, it switches immediately to 0. Here would be another example. I'm holding this pen at rest in my hand. What is its acceleration? 0. Then I let it go. The acceleration is obviously applied by gravity. So it switches from a 0 acceleration to a non-zero acceleration. Basically, we neglect the short amount of time that it would take. And the reason why is because we have the language to describe this. We talk about V, av is the change in position. We talk about A, av is the change in velocity. But we do not want to talk about delta A over delta T. We don't want to talk about how the acceleration evolves with time, so we have to cut it off somewhere. The act of changing your acceleration, delta A over delta T, that gets a name. It's called jerk. You can talk about the change in jerk over time. It's called jolt, and so far down the rabbit hole. Okay, but we got to cut it off at some reasonable place. So for us, since we don't talk about the change in acceleration, we just basically say you can change it very rapidly. You can change the instructions to the velocity very rapidly. You can pull your hand out from underneath the pen very quickly. You can switch your foot from the gas to the brake very quickly. Now, just because you switch the instructions does not mean that the velocity will immediately react. To give you an example, going back to that car example, when you have your foot on the gas and at that moment you're going 50 miles an hour, when you hit the brakes, the moment you touch the brakes, you're still going 50 miles an hour, right? So even though you switch the instructions, the velocity will take time to react. So now that you were going 50 miles an hour, when you have your foot on the gas, you were just about to go 51 miles an hour, right? Now that you put your foot on the brake, you're just about to go 49 instead, but you're still at that moment at 50 miles an hour. It's going to take time for your acceleration to change your velocity. Does that make sense? Okay. So just because we're allowing this, it still takes time for the velocity to react to the change in instructions. So we're seemingly going to have our cake and eat it too. We're going to make sure that the velocity change is continuous while the acceleration is allowed to flip. For instance, I'll give you an example. Again, going back to the pen. What's the velocity of the pen right now?